Okay guys, in this video lesson we're going to talk about ways that we can take this idea of a redox reaction and actually figure out what is the elements in there that are going to be oxidized and what are being reduced. It's really easy when we're dealing with ionics and ionic compounds because we can look at charge. But as soon as we start talking about molecules and molecular compounds and covalently bonding, it gets much harder. So to solve that problem, we're going to move away from using charge and actually go to something that's even better and more encompassing, which is oxidation numbers. Okay. So think of oxidation numbers as a way to figure out the electron capacity of all elements, whether they are ionically bonded or covalently bonded in a molecule. So we don't need to worry about charge anymore. In fact, it's actually a better way to view this because we know that we don't have pure ionic compounds and pure molecules. There's actually kind of a continuum there between the two. So there is some sharing, there is some transfer of electrons, a little bit of both going on at all times. Okay, so here's how we keep track of it. First thing we want to make sure is we realize is that when you are increasing the oxidation number, you're being oxidized, and when you are decreasing the oxidation number, you're being reduced. Okay, remember that Leo goes Ger, so when we lose electrons, that means we're going to be increasing our oxidation number, becoming more positive, and we're going to be oxidized. When we are Leo goes Ger, so when we're gaining electrons, we're going to be being reduced because we're going to be getting a more negative number. Okay, so one thing in the back of your head to keep in mind is that, remember, electrons are negatively charged. So when we gain electrons, we become more negative, and when we lose electrons, we become more positive. Okay, now there's rules to this. It's pretty plain and simple. You just got to follow your rules. Okay, so here is our rules that are up on the screen. In terms of what we have, you are fully capable of reading rules, so I'm not going to read them step by step for you as you take a look at these. However, what I am going to do is go to the board and we're going to take a look at several of these and we're going to apply all these different rules in different scenarios. Okay, so as we go here, we'll have the rules and then we'll take a look at the different possibilities as we go through each one of them. Right. So first thing we have is what do we do with single elements or simple elements like iron and diatomics like oxygen? Okay, so if you're a single element by yourself, no charge, you have an oxidation number of 0. Okay, if you're a diatomic, no charge, oxidation number of 0. Okay, so those are the pretty simple ones. They're zeros. Now, as soon as we get a compound like this, we go through the idea of if we have an ionic compound, we have a metal and a non-metal, they will follow their normal charge. Okay, so we can use our knowledge of charge to solve some of this information too. So magnesium and chlorine, magnesium we know is a 2+, chlorine we know is a 1-. So magnesium's oxidation state is going to be a +2, and chlorine is going to be a -1. Now notice 2+, 1-. When I do oxidation numbers, I flip my sign. Okay, it's a little detail, but it's one way for chemists to know that when are we talking about oxidation numbers and when are we talking about charges. So if we put the plus sign first, usually we're talking about oxidation. If we follow it, it's usually a charge. That's how we do it. Next one. So we have nitrogen and hydrogen. So here's the first time we get something kind of unique or something different, where we have nitrogen, which is a non-metal. We have hydrogen, which is a non-metal. So these are covalently bonded. This is ammonia. So there are no charges here. Okay, so we can't say this is going to be a -3. This is going to be a -1. It doesn't work out by charge. So instead, we go back to our rules. Okay, so for hydrogen, we're going to look at that one first because we have no specific rule for nitrogen. So we're going to base nitrogen off of what hydrogen can do. Hydrogen is always a +1. Unless it's a metal hydride. Okay, so right now it's not a metal with hydrogen, so it's not a metal hydride, so it's a +1. So if hydrogen is a +1, that means that the nitrogen, we have to make this thing neutral overall. So the oxidation numbers do need to add up to 0. Okay, so hydrogen's a +1, nitrogen has to account for that. So if we have a +1 and there's 3 of them, the nitrogen has to be a -3. Okay, which kind of matches its charge, which is kind of nice. Okay, so hydrogen's a +1, this is a -3. Going down to the next one, we have a metal, potassium, with hydrogen. Okay, so in this case, we have a metal hydride. So we have a metal hydride. We have potassium hydride. In this case, when you have a metal hydride, hydrogen isn't a +1, instead it's a -1. Okay, and potassium, because it's in an ionic compound, would be a +1. So our hydrogen here is a +1, and our potassium is a hydrogen, I flipped it. Hydrogen here is a -1, and potassium here is a +1. Okay, so hydrogen's oxidation state is very different than it was here. Okay, it's actually gained 2 compared to here in terms of the number of electrons that's associated with it. Now we move down to water. Okay, well we have hydrogen with oxygen, and hydrogen is not in a metal hydride, so hydrogen then has to be a +1. Okay, oxygen has its own rule also. Oxygen is always a -2. Okay, oxygen gets to have its own rule because it's one of the most electronegative substances out there. Okay, there's one exception to oxygen's rule. When oxygen forms peroxides, okay, hydrogen peroxide, sodium peroxide, potassium peroxide. So if we see a peroxide, we know that oxygen is only a -1. Besides that, it's always a -2. So in this case, oxygen has to be a -2. Let's see if that works out. Well, if hydrogen is a +1 and oxygen is a -2, let's see, +1, there's 2. Yeah, it makes a neutral setup again. Remember, we're not talking charge here, okay? This is covalently bonded, okay? This is not an ionic compound. These are not ionic charges. These are oxidation states, okay? So we're just assigning a number to them to identify who kind of owns the electrons right now in terms of those valence electrons. They are not charges here anymore. Going down to our bottom one, we have sodium with oxygen. And it looks kind of weird because we have Na2O2, which should look kind of weird to you because most of the time with oxygen, we see this doubling effect, right? It's like a 2-to-1 ratio because this is a peroxide, right? We have sodium peroxide. As a result, as a peroxide, oxygen takes on a -1 oxidation state. Sodium is going to be a +1 oxidation state. So our sodium, because it takes 2 of them to balance out the 1, is going to be a +1, and oxygen here is a -1. Okay, so this scenario here and this scenario here are pretty rare. These two are pretty rare scenarios, but they do exist, and they are worth mentioning because this is an exception for hydrogen and an exception for oxygen. Okay, coming over here, we'll continue kind of our idea, and we have sulfur with fluorine. Okay, so we have sulfur hexafluoride, which means again we're still dealing with molecules. Basically, from here on down so far, the molecule. These are all molecules. So we're not dealing with ionic charge anymore, but we can still assign oxidation numbers to them to give us an idea of what kind of electrons they own. Here we have sulfur, we have fluorine. Fluorine has its own rule also. So fluorine is always a -1. Always. It's the most electronegative substance. It will always, when it bonds into compounds, it will always pull electrons towards it, so it will always be assigned a -1, okay? Because fluorine's a -1, and there's 6 of them, that's a total of a -6 charge there, which means the sulfur, to make this thing neutral, has to have an oxidation state of +6, okay? That seems odd, because usually we think of sulfur having, a charge of -2, which is true. But keep in mind, if sulfur is bonding with fluorine and it's more electronegative, the fluorine is going to be pulling the electrons away from sulfur, right? So sulfur is not going to have as many as it normally has. So instead of the sulfur, trying to gain 2 electrons, it kind of gives away 6, all right? Now, again, not ionic compound, not ionic bond. It's still covalent. It's still sharing. But we're basically using numbers to represent the unequal sharing of these electrons. Sulfur is going to be gaining 1 electron from fluorine is going to be gaining 1 electron from the sulfur. Because there's 6 of them, the sulfur has to essentially kind of lose control of 6 of its electrons in this process, which gives it an oxidation number of +6. Now we have a polyatomic ion for the first time. Polyatomic ions are just like every other rule we've had, except for we have to account for the fact that we have 3 extra electrons here, okay? So instead of adding up to 0, like this had to be a total of a 0, this had to be a total of a 0, this had to be a total of a 0. Now, when we're done with this, it has to be a total of a -3, okay? So these two added up have to be a -3. Well, oxygen still follows its rules, so oxygen is going to be a -2. We have 4 of them, which means we have a total of -8 here, okay? So the overall presence of oxygen is -8. we had to end up being a -3, which means our phosphorus has to be a +5. Okay? So phosphorus, is a +5. The oxygen has a total of -8. So if we have, this times 4 is -8 plus 5 gives us a -3. So our total charge here ends up being a -3 between the two things. And again, shouldn't be too outlandish because phosphorus, we say normally wants to be a -3 charge. But again, in that magic rule of octets, being a +5 would be the other way of going too for that one. Okay? So oxygen's a -2, phosphorus is a +5. Now we come down to acetate. Okay, so acetate again is a polyatomic ion, and we have a -1 charge, which means that we have to work this one out. And I'm going to give us a little more room here now to kind of work it all out, because it gets a little bit more complex. So we, first of all, overall, when we add this up, has to be a -1. So we have our oxygen, we have our hydrogen, and we have our carbon. Okay, so when we get to ones that are a little bit more complex, maybe have 3 things in them with a charge, I like to break it down. So we have our 3 compounds, okay? Now the oxygen, it has a rule, it's going to be a -2. The hydrogen has a rule, it's going to be a +1. Carbon, we don't know what's going to be yet, okay? The oxygen, we have 2 of them, so we're taking that times 2. The hydrogen, we have 3 of them, we're taking that times 3, so we end up with a -4 here. We end up with a +3 here. Carbon, we have 2 of them. So whatever this is, it's going to be times 2. Okay? So we end up with this idea that a -4, a +3, plus whatever this is, has to equal a -1. Well, a -4 and a +3, they already equal a -1, which means this has to be a 0. So carbon actually has an oxidation state of 0, okay, in this scenario. And that's how we would figure it out, okay? So we know that our carbon was a 0, our hydrogen was our +1, and our oxygen was our -2 for this one, all right? Let's go on to calcium carbonate. Again, applying our rules, we have our calcium, we have our carbon, we have our oxygen. This whole thing has a charge is neutral. So ultimately, when we're done, they have to all add up to 0. However, we have carbonate here, which we know carbonate is a -2 total for its polyatomic ion, which means calcium has to be a 2+ for the metal. Okay, so if we go back to our original, actually go back to our rule number 2, where we have a metal with our polyatomic, so basically we have an ionic compound now again. When you have an ionic compound, that charge holds for its oxidation state. So we know, because it being an ionic compound, that calcium is going to be a +2. We know that oxygen is always a -2, except for peroxides. And there's 3 of them, so times 3 is a -6. We have 1 calcium, so this ends up being a +2. And we have a -6, which means this value in here has to end up being a +4. Okay? 2 + 4 - 6 = 0. Which means the carbon, since we have 1 of them, is going to be a +4 in this case. So carbon here is a +4. Now, another way of solving this, you could have ignored the calcium if you wanted to. And you could have said that carbonate, as a polyatomic ion, has to be a -2. So again, a +4 and a -6 will give you that -2 charge for your polyatomic ion alone. And then you can say, well, if this together is a -2, the calcium has to be a +2 to balance it out. All right? Last one, we have aluminum with manganese and oxygen. All right? Again, we have to recognize that this is an ionic compound. We have a metal and the polyatomic ion permanganate. All right. Now you might not know much about permanganate, and that's okay, because if you don't know its charge, you still can solve this. Another hint: you can look this up in the backside of your periodic tables. All right. So let's break it down. Aluminum, manganese, and oxygen. Aluminum in this scenario is going to have to be its charge, which is a +3. So we know that one because of it being a metal with a polyatomic ion. Oxygen is a -2 times 4. So -2 times 4 gives us a -8. Okay? So if we have a +3 and a -8, it's a neutral compound. So a +3 and -8, the manganese here has to be a +5 to balance it out. So we have a +3, a +5, and a -8. And now we get to a 0. Okay? So the manganese here is the only one that we really don't know and we're solving for and figuring out. The reason why we do all this is once you know these oxidation states here, if we change the compound or we react it with something, we can then refigure out the new oxidation numbers on the product side of reaction, and we can figure out what has happened to them. Okay? There is a whole list of additional practice for you guys to do to check out your skills on this, and we'll also have additional practice in class. Thank you.